Zoom session is being brought to you by the Fractal Recursive 12 star. All right, for today, uh, we'll be covering 1.5, 1.6, and 1.7. 1.5 is about word problems, 1.6 quadratics, and 1.7 other types of equations. Okay, word problems. Every time I teach a class in math, I get contradictory results. When people say, hey, can you find a use for this math you're teaching us? All right, fine. I say, here's some word problems. Oh no, word problems, people say. Why? Well, because word problems aren't really just math problems. They're translation problems. And a difficult translation problem at that. You start with a word problem. You translate to an algebra problem. You solve by various mechanical means, you get a solution, and you translate relatively easily back to a word answer. The hardest part, I mean, I teach mostly this with a little bit of that, but the hardest part is this, and it's the one which the book actually very rarely actually goes into. The problem being is that words are in English, and algebra is in algebra, and they're two very different languages, indeed very different kinds of languages. English is a natural language. It's run in everyday life and all sorts of things. It's actually highly poetic. It's a creative act to speak. Whereas algebra is synthetic. It's mechanical. It's as close as possible to a computer program. So it's as different. It just simply has a different structure. Um, and I note here, there's no formal algorithm to going from a word problem to an algebra problem, because if it would, then would already be algebra. So the best I can do is to go from something as elusive as a word problem to something as precise as an algebra problem is use your intuition. That's not much of an answer, I admit, but there are some basic things. First of all, the very first thing you really should ask is what is being asked for. That's sort of, how do you answer a question without knowing what the question is? And so in general, the thing to do is to give variable names to the question, to the names to the variables. Then there's also what are you being told? Again, important in answering any question. And there you want to assign names to the parameters and also to identify what the parameters are. Then how does what you're told relate to what being asked for? Well, that's not the trivial part at all. And there are various ways. You can draw diagrams, you can draw tables, you can write an equation, which is something called rhetorical algebra, which is half English and half algebra. I could say ask the next question, but it is, of course, incredibly vague, but it really is the best thing you can do. So you ask question after question, and you can write an algebraic equation, you hope the right one, and then at that point, things can get precise and you can solve it. So for example, from 1.5, here are some word problems. A rental company charges $65 per day plus 20 cents per mile. Michael rents a truck for 3 days and his bill is $275. How far did he drive? Okay, fine. How far? That's a D for days. That's the unknown. C is the charge. That's what we're told about. And D, distance driven, is what's being asked for. Now, $65 a day means the charge is 65 times capital D for the number of days, plus 20 cents a mile, 0.20 little d. That's charge in terms of days and distance. And of course, it's important to make sure that you get $0.20 per day, right? Well, it's 20 cents per mile, 20 cents per mile, and make sure that these units line up. The days is 3, capital D is 3, C charges 275. So you're plugging in and you get 275 equals 65 times 3 times point plus 0.2D. And now we have our equation. So at this point, you can start being precise. 65 times 3, what's 195? 275 equals 195 plus 0.2D. Subtract 195 from both sides, you get 80 equals 0.2D. Divide by sides by 0.2 and get D equals 400. So, and then this is the important part, distance equals 400 miles. It's considered good etiquette to answer the question and of course mark it in roughly the same language that it was being asked. It's not quite enough to write D equals 400. It's a little bit better to say that the distance is 400 miles because, like I say, it's polite to answer in English if you were asked in English. What annual interest rate on an investment of $3,500 yields $262.5 interest in 1 year? Okay, P is the principal, that's 3,500. T is time in years, 1. I is interest, 262.5. R equals the interest rate. Now the equation there, given in the book, is interest equals principal times rate times time. This is for simple interest. Later on, I suppose I should have said simple interest, whatever. Okay. Later on, we'll get to compound interest, which is much more complicated. I equals PRT. Interest earned is 262.5. That goes there. T time is 1 year there. P 3,500 principals, it goes there. So 262.5 equals 3,500 times 1 times R. Okay, at this point, it's a simple matter of dividing. Divide both sides of the equation by 3,500. 262.5 over 3,500 equals R, which equals 0.075. Now, they ask for interest rates and percentages. So you write that as 7.5% annual interest rate. And again, it's considered too polite to write as something like this in something like English, rather than merely this in algebra. Here we have a rectangle, 25 feet wide and x feet long. Its area is 1125 square feet. What's the length x? Well, all right. Area equals A equals area, W equals width, X equals length, A equals W, X is the equation. There's an equation. And we're given that A equals 1125 and W equals 25. So 1125 equals 25X, and at this point, the algebra kicks in. Divide both sides by 25, get X equals 45. So the answer is the rectangle is 45 feet long. Here we have what's called a mixture problem. They have a lot of these. There are 5 rings, each weighing 18 grams, are at 10% silver and 90% gold. The jeweler melts them down and adds enough silver to reduce the gold content to 75%. How much silver was added? Okay, the total weight of the 5 rings is 5 times 18. It's 90 grams. 10% of that is 5 grams of silver. The 90% of that is 81 grams of gold. Now here's what we have. We want to add X grams, that's the amount, how much silver, X grams. And so that'll be, let's see, it's 81 grams of gold over 90 plus X grams total, because we're starting with 90 total and adding X grams of silver. 80 over 90 plus X is 75%. 81 over 90 plus X equals 70.75. Here's the equation. So, okay, we solve it first by transposing 90 plus X. So 81 is equals 0.75 times 90 plus X. Divide by 0.75, 81 over 0.75 equals 90 plus X. This comes out to be 108. 108 equals 90 plus X. Subtract 90 from both sides. 108 minus 90 equals X. X equals 18. So add 18 grams of silver. Now here we have a quantity, a rate time problem. Candy and Tim share a paper route. I assume that Candy starts from one end and Tim starts from the other. It takes Candy 70 minutes to deliver all the papers, and it takes 80 minutes to deliver them all. If work rates add, if they work together, just a moment, when they work together, 5, 5, 7, they work together. Apologies for the typo. And assuming, like I say, that Tim and Candy work from opposite ends, and that means the work rates add, then how long will it take them to deliver all the papers if they work together? All right, fine. The equation in question is quantity equals rate times time. And you'll notice that this is a case of what I call it, rhetorical algebra, because here are words, but here are mathematical symbols. Okay, rate equals quantity over time, and time equals quantity over rate. That follows from this. Now her rate is 1 root per 70 minutes. His rate is 1 root per 80 minutes. And so if their work rates add, so the combined rate is 1/70th plus 1/80th of a root per minute, which after a bit of arithmetic comes out to 3 over 1/12 of a root per minute. Okay, that's the combined rate. The combined time is 1 root divided by the combined rate. 1 root divided by 3 over 1/12 root per minute, which comes out to 112 over 3 minutes, or in other words, 37 1/3 minutes.